Hey guys, welcome. In the previous episode, we have seen the definition of neural network. We have seen the importance of weights and biases. We have seen how to choose the best fit line or the best fit equation for our neuron. Up to now, our data points are following a linear pattern. What happens if our data points look like this? Now here, no matter which combination of weights and biases we take, we won't be able to find a best fit line for this distribution, because here we are taking a linear line or linear function, but our data sets, they follow a non-linear pattern. Now I will say like, hey, listen, currently we are working with only one neuron, but in neural network we have bunch of neurons. Let's build a neural network with multiple neurons to deal with this non-linear distribution. And you are correct. Let's build a neural network to deal with this non-linear distribution. Now, this is our pattern, and this line represents the equation of a single neuron. You can see this is our neuron and this is the equation of this neuron. Now, if we build a neural network using multiple neurons, it will look like this. So here N1 is the equation of this neuron, and N2 is the equation of this neuron, then N3 is the equation of this neuron. So here you can observe N3 is taking the outputs from N1 and N2 as inputs. Similarly, N4 is taking the outputs from N1 and N2 as inputs, and then N5 is taking the outputs from N3 and N4 as inputs. That means N5 neuron is giving the final output for this neural network. So equation of y dash will look like this, and you can see here this is equation of N1, this is equation of N2, and you can see this is N3 and this is N4, and then everything is combined together to give the equation of y dash. Now let's take some values for these weights and biases of this network. When we take some values, the equation becomes this, and this is the output from this network. You can see this is also a straight line. So what happened here? It turns out when we simplify this equation, it will become the equation of a single neuron. Still confused? Let's go back to the equations of our neurons. So we have our network and we have our neurons. Now you can see all these equations are linear equations. Hence, all these neurons will learn a linear pattern. So basically, x1 is given to this n1 and x1 is given to this n2, and they think the pattern looks like this. And output from these two neurons are fed to the next layer of neurons. This neuron is working on the information given by these two neurons. So this is thinking the output looks like this, and this is thinking the output look like this, and hence it is kind of compensating between these two, and it is thinking the output looks like this. Similarly, this neuron is thinking the output looks like this based on the information collected from N1 and N2, and the outputs from these two neurons are fed to the final neuron, and this neuron thinks the output will look like this. Hence, no matter how many neurons we have in our network, with these linear equations, we are unable to fit the nonlinear distribution. And this is the reason why the final equation of this network is similar to the equation of a single neuron. Now I will say, hey, you told us earlier that we use neural network to deal with images, to deal with videos, to deal with text, and all this data, they are highly nonlinear in nature. Then what to do? It turns out to deal with this kind of nonlinearity, we have something called activation function. Now what are these activation functions of neural network? An activation function in deep learning is a mathematical operation applied to the output of each neuron in a neural network. You can see here. Now when we use activation function in hidden layers, we introduce nonlinearity to the network. When you use activation function in the output layer, we get outputs in a record format or in a record range. And don't worry about this application of activation function in the output layer. We'll be learning that in the later video. Right now, focus on the application of activation function in the hidden layer. And this is how we'll find our solution for this nonlinearity issue. So there are a bunch of activation functions available, you can see here, and you can go to this Wikipedia link. I will give the link in the description. And also by looking at this graph, you can get an idea of the input and output of these activation functions. And you can see here, when we give x as input to this identity activation function, we'll get x as output. And when we give x to this binary activation function, here if x is less than 0, we'll get 0 as output, and when x is greater than or equal to 0, we'll get 1 as output. Similarly, you can see the output varies from activation function to activation function. Now you can see here, currently in our neural network we are using this activation function, and that's the reason we are unable to learn nonlinear pattern that is present in our dataset. You can go to this link. So this is also another link which has great explanation on activation functions, and you can check this link also. Now let's take ReLU to deal with this nonlinearity we have in our dataset. This is because it is kind of, you can see this is a combination of two straight line. So basically we are getting a nonlinear distribution here with very less calculation. So in ReLU, when x is less than 0, we are getting 0 as output, and when x is greater than 0, we are getting x as output. Now let's check the effect of activation function or effect of ReLU on a neuron. So this is our neuron. You can see we have this neuron and we have this equation wx plus b, and here w equal to 1 and b equal to 0, and this is the output from this neuron. You can see this is a linear output. So here when we have x equal to -1, you can see we have -1 as the output from this equation. Similarly, for all values of x, we are getting x as output. Now when we use ReLU, the equation looks like this. You can see when x is less than 0, we have 0 as output from ReLU, but we have x as output from the linear equation, and when x is greater than 0, we have the same output from both the equations. Now let's have a look at the behavior of these two equations when we change weight and bias. As you can see, when we change the weight, this is the effect on both the equations. So this is without ReLU and this is with ReLU, and when we change bias, this is the effect on these two equations. So one thing to notice here, no matter which combination of weight and bias we take, we cannot move this graph from x-axis. So this is one limitation of ReLU when we are using ReLU on a single neuron. Okay, Now let's create a bunch of neural network with ReLU in the hidden layer, and then let's see how they try to fit this nonlinear data we have. So basically I have created different neural network with different set of neurons, then I have trained them to fit this nonlinear data. So this is the network we have currently. We have two number of neurons in each layer, and this is, you can see, this is the PyTorch code for this network, and the blue dots represent the nonlinear data points in our data set, and the red dots, they represent the prediction from this network. You can see here also blue line represents the training loss and the red line represents the test loss. So basically I ran the network for 500 number of epochs. So here we have three number of neurons in each layer, a slight improvement on the previous network. You can see here, by just adding one neuron to this network, we can have a good fit on this nonlinear data. Now here we have 4 neurons in each layer. Now we have 5 neurons, you can see here. Now we have 10 neurons. So you can observe here, with addition of neurons, it becomes easier for the model to learn this nonlinear data. So this is another network. Here we have 2 neurons in each layer, and we have 1, 2, 3, 4, 5. We have 5 hidden layers here. this network we have 5 number of neurons in the first 3 layers, and then we have 2 number of neurons in the last 2 hidden layers. Now we have 32 number of neurons in these first 3 layers, and then we have 8 numbers of neuron in this last 2 hidden layers. One observation here is that with increase in number of neurons, the learning of neural network becomes faster and easier. Now here we have 256 number of neurons in our network. Guys, it will be a big network, and I was unable to plot that network here, hence I left it blank. But you can see the effect here. So it learned the pattern within like 5 to 10 number of epochs as compared to other network. And you can see this is the effect of using activation function in hidden layer. Now the question is why? Why does ReLU work? Let me rephrase that. Why does activation function work? To understand this, let's understand the behavior of ReLU when we have a single neuron and when we have multiple number of neurons. Now here we have our neuron and we have our ReLU activation function, and this is the output of this neuron. And you can see now when we have x is greater than 0, the neuron gets activated, you can see, and when we have x is less than 0, the neuron gets deactivated. Now this is called the activation point. That means when we are moving from -1 to +1, beyond this point our neuron is giving some output, and before this point the output of our neuron is 0. So when a neuron is giving some output, whether it can be positive or negative, it is activated. When the neuron is giving 0 as output, it is deactivated. You can see the effect of weight on this neuron and the behavior of this neuron, and you can see the effect of bias as well. So by controlling the bias value, you can clearly see we can control the activation point. So earlier, let's go back. Earlier it was the activation point was at 0, and now when we control the bias, you can see we are changing the bias. We can shift the activation function from 0 to any other location. Now let's create a network with 2 neurons. And you can see this is our equation of the network, and you can see here we are applying ReLU on this hidden neuron. This neuron is represented by this graph and this neuron is represented by this one. We can say that this graph gives the final output of this network. So when we have W equal to 1 for both the neurons, this is the behavior. You can see now both neurons are activated. So here we are changing the weight of first neuron. You can see the effect, and weight of second neuron here. Here you can see we are getting negative value as output from the second neuron. This orange color indicates that the neuron is giving negative value and it's activated, and this one blue indicates the neuron is giving positive value and activated. Now when we change the value of bias for second neuron, you can see here we are able to move this line from the x-axis. And remember, this was the limitation of ReLU when we are dealing with only single neuron. Now let's add another neuron to the network, and this is the distribution of the neuron in this network. And you can see we are applying ReLU on the neurons of this hidden layer. Now here all the weights are 1 and all the biases are zeros. And you can see the output from these two neurons are fed to the last neuron. You can see the output neuron. Hence you can see the effect here also. This is the output we get when we add these two values. Now when we change the weight of first neuron, you can see this is the effect on the output of this network. So by changing the weight and bias of first neuron, we are able to get this kind of shape out of this network. Similarly, when we changing the bias of second neuron and the bias of third neuron, you can see we are able to get this shape, and also we are able to shift this graph from x-axis. So by combining multiple neurons, we are able to mitigate or overcome the limitation of ReLU, and we are able to get different kind of shapes from the combination of different kind of weights and biases. And you can see here when we are at this point, you can see these two neurons are activated, and when we are at this point, you can see these two neurons are activated. That means in a neural network all the neurons are not activated all the time. So at a particular time some of are activated and some of are deactivated. So this is the reason why ReLU works. That means when we use activation function in a neural network, we are able to approximate any nonlinear distribution. Remember this network. This network was able to fit this nonlinear data perfectly. Let's see how each and every neurons of this network work together during training to fit this data, or should I say to learn this nonlinear pattern. Now here at the beginning of the training, all the weights and biases are getting initialized, and now the training starts. Here we can see we are adjusting the weights of first layer, and then we are adjusting the biases. this is how this network was able to learn the nonlinear pattern in our dataset. So guys, I hope you understood the importance of activation function in neural network. That is how neural network is able to deal with nonlinear data in the real world scenario. In the next episode, we'll be talking about losses of neural network. So, like, subscribe and share. I'll see you in the next episode. Till then, take care.